Can you hear me all right? Good morning. Is this recorded? Yes, it is. Okay, very good. Welcome this morning. I'm Joanne Bundy. I chair the Community Education Council and with the sponsors of bucket courses. And the planning committee joins me in welcoming you all to the fourth class of the bucket courses variety pack. That isn't easy to keep straight. If you will silence your cell phone, I will make one small announcement that if you want to have a DVD of any one of these lectures, you can talk to Jack Gustafson. There's a sign-up sheet on the table out in the hall, and they are $5 each. And you can get, even back to Tilly Woodward's, you can get the DVD from any one of the classes. Well, it's deja vu all over again today. We have, we have Beryl Clotfelter, who was the very first lecturer that we had when we started the bucket courses 5 years ago. He taught an 8-week course on our universe, how do we know? We were hoping to have about 20 people and we had 43. And thanks to Mary Lou, Beryl was able to dummy down the class enough so that we could all understand it. And all 43 of those people hung in there. And as you can see, the attendance has increased ever since then. So we are delighted to have Beryl back again. Beryl has a PhD in physics and mathematics from the University of Oklahoma. He is Professor Emeritus in physics at Grinnell College, and we are delighted to have one of the college's most beloved professors with us this morning, teaching us about
It's on the screen.
Beginning of the scientific enterprise. When you have 6 weeks in a row, it's hard to keep the title straight. So here is Beryl Clotfelter.
Okay, how's the sound? Okay. We are all familiar with the idea that science isn't too loud. Now, how's this?
That's better.
Okay, we all know that science is an enterprise. That is, it's an organized activity. We think it's legitimate to say that a person will make a career in science, and we know that science is an important part of our society. One indication that science is an active enterprise is the existence of scientific societies and scientific journals to publish the results of scientific research. Unless you are engaged in some kind of scientific activity, you may not have any idea how many scientific societies and journals there are. Probably no one really knows. But there are hundreds, probably thousands of societies, and certainly thousands of journals. Some journals are general, publishing material from many fields. A prime example is Nature, a prestigious British journal that publishes all kinds of material. Another is Science, that's just Science, which is the publication of the American Association for the Advancement of Science, or AAAS. The AAAS was founded in 1848 and is the largest general science society in the world. It's estimated that the readership of science is about 1 million persons. Some scientific societies are well known, like the American Medical Association. And probably most people know JAMA as the Journal of the American Medical Association. Many people probably also know about the New England Journal of Medicine, which is not published by the organization. On the other hand, very few people may have heard of the Astrobiology Society of Grinnell, or the American Arachnological Society, or its publication, the Journal of Arachnology. Arachnologists study eight-legged critters like spiders. At one time, I belonged to the American Physical Society, the American Journal of Physics Teachers, and the American Association for the Advancement of Science, the AAAS. It has not always been so that we have so many societies and journals. And I want to go back to the 17th century, mid-17th century, and look at the beginnings of scientific activity. Science did not begin in the 17th century. Some good science had been done in classical times. Everybody knows about Archimedes' principle, which goes back, of course, to classical Greece. Some science was done in the Middle Ages, both in Europe and perhaps even more in the Arab world. And by the time we get to the mid-17th century, we've already passed Copernicus, Kepler, Brahe, all good scientists. However, some things happened in the 17th century that I think make it appropriate to look at that time as the beginning of the scientific enterprise as a general organization. Now let me set the stage just a little bit. In England, every student of English history knows about 1660. That's the year that Charles II was restored to the throne of England. Charles I had been executed in 1649. Charles II was restored in 1660, and it seemed to be sort of a return to normalcy. Some very important dates have been passed scientifically. Kepler published 3 laws of planetary motion, and the third was published in 1618. In 1620, Francis Bacon published the Novum Organum. In 1628, a very important work was published by William Harvey, a British physician, on the motion of the heart and blood. This was the first demonstration that the blood circulates through the body. Previously, it had been thought that the blood is simply produced, pumped out of the body, and absorbed. And Harvey demonstrated that the blood circulates, chiefly by quantitative calculation. In 1632, Galileo published 2 world systems, comparison of Ptolemaic and Copernican systems. And in 1638, he published 2 new sciences, the beginning of physics. And in between those, Descartes published Discourse on Method in 1637. Then we come to 1649, Charles I executed, 1660, Charles II restored. In 1662, the Royal Society of London was chartered. In 1665, it began publishing its proceedings called the Philosophical Transactions. And in 1657, Spratt published a history of the Royal Society, and then 1687, Newton produced the
5
Principia.
years later. Short book. What's the short?
In the second half of the 17th century, men all over Europe, but particularly in England, began meeting to discuss their scientific experiments and their results. There were organizations loosely formed in a number of British cities. But the one that turned out to be the most important was in London, where a group of men had been meeting for several years. And then in about 1660, decided to organize. 12 of them decided they would try to get a charter and they'd form an organization. They became known as the Committee of 12. Of the 12, only 2 are well known to most of us. One is Robert Boyle, who's considered the father of chemistry. You probably remember Boyle's law from physics or chemistry or something. The other was Christopher Wren. Now, Christopher Wren was a remarkable man. He was a mathematician, physicist. What's he best known for? Architect. After the Great Fire of London, he rebuilt more than 50 churches in London. And most importantly, St. Paul's Cathedral. Well, the Committee of 12 drew up a list of about 40 other men who should be invited to become paying members, and so the number grew rather quickly. They petitioned King Charles II for a charter, and it was granted. And then they could call themselves the Royal Society. The title given in the charter was the Royal Society for Improving Natural Knowledge. Probably they hoped for some financial support from the king, but in that, they were mostly disappointed. Richard S. Westphal, he taught at Grinnell College about 50 years ago, known to all his friends as Sam. The historian of science said this: Charles II's purse always was insufficient to the demands made upon it. Faced with the choice of supporting Nell Gwynn, his mistress, or science, he never wavered in his duty. And the adjective royal was by far the most valuable contribution that the Royal Society received from him. Despite his name, and despite the official sanction given by the charter, it was a private organization in the fullest sense. Evidently, there was some criticism and some unease expressed, particularly by the clergy, about the new project. And so almost immediately, the members engaged Thomas Sprat to write a history of the Royal Society. What he wrote would be better classed as apologetics rather than history. He explains what they're doing and tries to defend them against criticism. Very soon after the Royal Society was founded, it began publishing a journal, The Transaction, which is still being published, making it the oldest scientific journal in the world. The formation of a society to encourage scientific activity was not without some precedent. In 1603, such a society was formed in Italy, and it lasted until 1630. Another such society was formed in Italy in 1657, and it lasted 10 years. 4 years after the Royal Society was formed, a society was formed in France, the Academy of Sciences, by the authorization of Louis XIV, as a part of the government. The French limited membership to people who had some claim to be scientists. The British accepted amateurs. Now I want to look at Sprat's history of the Royal Society. Here's the first page. At this time, they were still using the old Gothic S which looks like an F, either a half crossbar or no crossbar. And so you see places where, like up here, history of the institution, design, and progress of the Royal Society of London for the advancement of experimental philosophy. And the next part, I shall here present to the world an account of the first institution of the Royal Society and of the progress which they have already made, in hope that this learned and inquisitive age will either think their endeavors worthy of its assistance, or else will be thereby provoked to attempt some greater enterprise, if any such can be found out. Spratt began with a very flowery introduction, dedication to Charles II, that ends, "Your Majesty will certainly obtain immortal fame for having established a perpetual succession of inventors." Now, Spratt realizes that some readers may wonder why he is presenting a history of something that has been in existence for less than 5 years. So he tries to answer that question. Besides this, I can also add in my defense that though the society of which I am to write is not yet 4 years old, and has been a necessity hitherto chiefly taken up about preparatory affairs, yet even in this time they have not wholly neglected the principal end, but have had success in the trial of many remarkable things, of which I doubt not that I shall be able as I pass along to give instances enough to satisfy the curiosity of all sober inquirers into truth. Oh yeah, it did like. Now we'll go back. And in short, if for no other end, yet certainly for this, a relation of their first original ought to be exposed to the view of men, not like by laying down on what course of discovery they intend to proceed. The gentlemen of the society may be more solemnly engaged to prosecute the same, for now they will not be able handsomely to draw back and to forsake such honorable intentions, when the world shall have taken notice that so many prudent men have gone so far in a business of this universal importance, and have given such undoubted pledges of many admirable inventions to follow. Spratt said that he had intended the book to come out sooner, but it was delayed by two disasters: the plague that struck London in 1665, and the Great Fire that destroyed much of London in 1666. Spratt began with a discussion of science in the ancient world, and concluded that the investigation of nature reached its highest point in Athens with such philosophers as Plato and Aristotle. However, the Greeks were not much inclined to do experiments, and most of their science was based upon observation and then deductions from general principles. Spratt says that this method of procedure, positing general principles and then drawing deductions from them, has been the common method of doing science up until this time. He says this method is fine for mathematics, where you want to draw logical conclusions, but is not very good for investigating nature. What the founders of the Royal Society proposed to do is to carry out deliberately designed experiments to answer specific questions. In some cases, they will choose a subject and compose questions. They will gather up all their knowledge about it and their ignorance, and then designate somebody to carry out experiments and report back at the next meeting. At their weekly meetings, experiments were always done so that everybody could watch, and then they would discuss what had been improved, what needed to be done to further improve this knowledge, that sort of thing. This use of carefully designed experiments to answer specific questions was something new in the 17th century. Spratt explicitly said that they do not intend to deal with theological issues. I think this section, in his defense of the Royal Society, makes the point. The objects of men's thought can be only three things: God, men, or nature. They're not going to deal with God. They will meddle no otherwise with divine things than only as the power and wisdom and goodness of the Creator is displayed in the admirable order and workmanship of the creatures. In men may be considered the faculties and operations of their souls, the constitution of their bodies, and the works of their hands. Now, by souls, he seems to mean pretty much what we usually say the mind. They're not going to talk about souls. I admit that. Politics, morality, and oratory are already dealt with adequately elsewhere. Reason, temper, will, passions of men are hard to reduce to observations and afford much room for observers to falsify and counterfeit. An investigation of those subjects would lead them into talking instead of listening, and they were very much determined not to get bogged down in just talking. They wanted to do things, see things, and know where they were going. So they ruled out what we would call the social sciences. These two subjects, God and the soul, being only forewarned. In all the rest, they wander at their pleasure. In the frame of men's bodies, the ways for strong, healthful, and long life. In the works of men's hands, those that either necessity, convenience, or delight have produced. In the works of nature, their helps, their varieties, redundancies, and defects, and in bringing all these to the uses of human society. The best way to get some insight into what the founders of the Royal Society considered important is to look at the Philosophical Transactions, the publication. Here is the first page of the first issue. Philosophical Transactions, Monday, March 6, 1665. Contents, and then an introduction. Here is the contents. Now, I suspect you can't read that very well. So I'm going to summarize the important parts. It contains an account of the improvement of optical glasses at Rome. Observation made in England of a spot in one of the belts of the planet Jupiter. Of the motion of the late comet predicted. A relation of a very odd, monstrous cat. Of a peculiar lead ore in Germany, very useful for essay. Of the new American whale fishing about the Bermudas. A narrative concerning the success of the pendulum watches at sea for the longitude. A catalog of the philosophical books published by Monsieur de Fermat, lately dead. What we see in these contents is typical of much of the early scientific publications. Most of the people contributing were naturalists, not analytical scientists. There were no developed criteria for what should be included or how papers should be written. Hence, we see a paper on the improvement of the making of glass. Observations of the planet Jupiter and the comet, along with the relation of a very odd, monstrous cat. I'll spare you the anatomical details of the cat. The last item is a catalog of the books published by Fermat. He actually died on February 12, 1665, about 2 months before the publication of this journal. Fermat was a mathematician, and if non-mathematicians know him at all, it's probably because of Fermat's conjecture or Fermat's last theorem, which you may know about. I will call your attention to a narrative concerning the success of the pendulum watches at sea for the longitude. I presume you know the problem of determining the longitude of a ship that has been at sea for months. A navigator can see when the sun is directly overhead. If he knows when the sun was directly overhead at Greenwich, he can calculate his longitude. The problem is knowing when the sun was overhead at Greenwich, if he's been at sea for a long time. Well, the obvious way is to carry a watch or a clock that will keep Greenwich time. This is a report of a test at sea of a pendulum watch made by Christian Huygens. Now you can imagine the problem of a pendulum clock on a ship. It doesn't work too well, but this is not entirely satisfactory. In fact, 50 years later, Parliament offered a prize of £20,000. That was equivalent to millions today, for anybody who could solve the problem of determining the longitude of a ship that had been at sea for months. And 50 years after that, John Harrison won the prize with his marine chronometer. If you don't know that fascinating story, I urge you to look at a small book, really very small, by Davis Sobel with the title Longitude. It's a fascinating read. Standards of what would be significant in the quality of reporting had not been established. And the result is that some of the entries seem extremely strange to us. For example, the issue of the Philosophical Transactions for May the 8th, 1665, includes a short note about how they killed rattlesnakes in Virginia. Again, I don't think you can read that very well, so I'm going to give you the gist of it. Remember, rattlesnakes are indigenous to the Western Hemisphere. They don't have rattlesnakes in England or Europe, so they were intrigued by rattlesnakes. During a discussion of rattlesnakes, Captain Silas Taylor related how they are killed in Virginia. A wild plant in Virginia, like pennyroyal, has leaves have a pungent odor when they are crushed. Crushed leaves are put into the split at the end of a long stick and held at the nose of the rattlesnake. The snake tries hard to escape, but if it can't escape, the leaves are held there, he dies after about 30 minutes. This was done in July 1627. Now let's think about this. A man catches a rattlesnake. He wants to kill it. Somehow he keeps it, pinnings it, and he goes and hunts this weed, He gets some leaves and crushes them. He finds a long stick, puts a split in the end, puts the leaves in there, pulls it in the snake's nose, and after about 30 minutes it dies. Why didn't he just chop its head off the garden? I wonder if some amused Virginian was having fun at the expense of a gullible Englishman. There was a great deal of interest about freaks of nature. And in 1665, a report was published with the heading, Observables on a Monstrous Head. Mr. Boyle reported a calf that had no nose, and the two eyes were joined together because there was no nose between them. The eyes had separate corneas, but only a single optic nerve. Now, here's a report I found particularly striking. An intimation of a way found in Europe to make china dishes. Notice was lately given by an inquisitive Parisian in the inn of his in London that by an acquaintance he had been informed that Senor Sampaio, a canon in Milan, had the secret of making as good porcelain as it is made in China itself, and transparent, adding he had seen him make some. This as it deserves, so it will be further inquired after, if God permit. How is that for reliable reporting? Somebody told me that he'd been told by somebody else that something happened. But it's an important subject. So I'll try to find out more about it if God permits. It sounds more like a game of telephone. You can imagine the response the editor of a scientific journal today would give to that kind of a paper that is submitted. I think that this might be a good time to take a 10-minute break. So let's break, come back to continue.
And now we'll begin the second half of Beryl Clotfelter's lecture on the beginning of the scientific enterprise. Beryl Clotfelter.
I don't think the sound not working. That's right. Is that one? Okay, now, thank you. I was asked about why there were no scientific society before about 1660. Individual scientists like Galileo, Kepler, either corresponded by letter, private letter, with others doing similar work, or they wrote books. The reason I've called this the beginning of scientific enterprise is we're moving from the time of individual scientists who correspond by private letter, or they write a book and they have a lot of work done, to a time when there is continuing discussion in groups organized for that purpose. This is something that is beginning particularly with the Royal Society, although there have been some in the Italian societies earlier, but it is a new movement. And partly the reason is that the method of doing science is changing. The use of experiments designed specifically to answer a particular question. And that is new. I'm going to tell you about a few reports in the philosophical transactions. There's a story about a young girl, about 13 years old, who from the time she was 6 and began to help her mother in the kitchen. Would, whenever possible, fill her pockets with salt and eat the salt the way other children ate sugar. As a result, she became so dried out and so stiff that she could not stir her limbs and thereby starved to death. The author of a note said that 20 years ago, he was told by an apothecary in Cambridge that he himself had left the blood from a man's arm by the order of a physician. The man's blood was white as milk as it ran out of his arm. It had a little dilute redness, but immediately as it fell into the vessel, it was perfectly white. When it fell on the floor, it was like drops of milk. The conjecture of the physician was that the cause was that the man had been much fed on fish. I really should call on the two doctors at the back to explain this. I won't put them on the spot now. A number of papers described these experiments in which materials were injected into the veins of animals. When nitric acid was injected into the veins of a dog, the dog was much distressed and died. His blood was found to have coagulated. When sulfuric acid was injected into the veins of the dog, it too died, and blood had coagulated. But when oil of tartar, which I think must have been a solution of potassium tartrate, was injected into a dog's veins, the dog died, but the blood was found to have become very thin. The conclusion drawn was the animal dies if the blood coagulates or if it becomes excessively thin. Wine and milk were also injected into the veins of animals, and in some cases, into the veins of men. The results were not very satisfactory. Now, you may wonder, didn't they know what the blood is for? Didn't they know about it carries oxygen? No. Oxygen would not be separated, named, for another century. Its role in combustion and in respiration, use in animal cells, would come in the 19th century, not the 17th. They didn't have a clue what the blood was for, what it did. And they were just trying anything they could to see what happened. There are many papers concerned with the making of glass and with the improvement of telescopes. The telescope had been invented by Galileo. The reflecting telescope was just being invented. But there was a great deal of interest in improving telescopes, doing things to get a better image. And then in among the reports that cause us to chuckle are reports of some very good and important science. One such report, dated January 1st, 1665, is titled "Of a Prominent Spot on Jupiter, by which is manifested the conversion of Jupiter about his own axis." After reporting that the shadow of one of Jupiter's moons had been observed moving across the face of Jupiter, Mr. Hooke first and then Mr. Cassini said they had seen a prominent spot on Jupiter. And by watching the spot, they could see that Jupiter turns on its axis, and they estimated the time of rotation at 9 hours and 56 minutes. This is the first report of the great red spot on Jupiter, which is still visible today. NASA's probe to Jupiter was named Cassini for that astronomer. The transfusion of blood was a subject of great interest, and there are several papers about the transfusion of blood, one animal to another. But one paper of particular interest was published in December 9, 1667 under this heading, an account of the experimental transfusion practiced upon a man in London. This was an experiment carried out on Mr. Cogan, C-O-G-A. And the report says, in the presence of many considerable and intelligent persons, those two learned physicians and dexterous anatomists, Dr. William Moore and Dr. Edmund King, report that they cut into the carotid artery of a young sheep, and they let about 12 ounces of the sheep's blood run into a pitcher. Then they cut open a vein in the man's arm, put in a tube, and poured in the sheep's blood. And they estimated he got 10 or 11 ounces. He felt so good after the process, he wanted them to repeat it in 3 or 4 days, but they thought they ought to wait a little bit longer. Now we know from other sources that Mr. Clotfelter had mental problems, and the transfusion was done using the blood of a lamb in the hope of calming him. Actually, he had a severe reaction, although he lived. Most of the experimental blood transfusions of humans at that time were done to treat mental conditions, not physical conditions. But there is an account of a successful transfusion to treat a physical condition. A young man was given the arterial blood of a lamb and cured of an extraordinary lethargy, consequent to having had a severe fever, during which he was bled 20 times. Now, the report does not say how much blood was drawn, but we know if we go forward into the 19th century, bloodletting was common medical treatment. The amount of blood was frequently about a pint. Let's suppose, on an average, a cup of blood was drawn from this man 20 times. That's 5 quarts, which is about what the human body holds. We don't know over what period of time, maybe several weeks, but it's not surprising he'd go lethargic. He'd been almost bled to death. And apparently the sheep's blood cured him. Now, a skeptic argued that it was not the transfusion that cured him, but the fear of it, what he called the apprehension of the process. But the man writing the report said that's not true. If he'd been cured by apprehension, he would have been cured 24 hours later, when he had great apprehension because he fell down the stairs. Another report from Danzig, translated from the Latin in which it was originally written, tells of the injection into the vein of a soldier dangerously ill with venereal disease, of a laxative, which caused such pain in his arm and elbow and swelling of the little valves in his arm that the arm had to be massaged until the swelling went down. But the laxative did have the desired effect. We know from other sources that some of the humans who received animal blood died, which is why you do not get sheep blood today if you get a transfusion at the hospital. It's also why Parliament prohibited blood transfusions, and no more work was done in that field for about 150 years. There are reports of persons struck by lightning and killed or injured, observation of comets, of minerals, and reports of observation with the newly invented microscope. is Henry Oldenburg. He was secretary of the society. He was a German, trained in theology, who went to England as a diplomat in 1653 and stayed there. He was one of the early members of the Royal Society. He had extensive correspondence, private, with scientists all over Europe. As secretary, he became editor of the Philosophical Transactions. As I look at the transactions after the first year, there's a remarkable change. The kooky articles disappear. Some of the articles may seem a little strange to us, but they are all good, legitimate science. I don't know what happened, but Henry Oldenburg is given credit for instituting peer review. And I can imagine something like this. Henry went home from the office one day and said to his wife, "You can't believe some of the stuff the gentlemen of the society think should be published. Unless I can find some way to screen out that stuff, the transactions are going to become a laughingstock." His wife said, "I have a suggestion. Tell the men of the society that when a paper is submitted, you will ask 2 or 3 other members to look at it and advise you about whether it should be printed, or changed, or rejected. You might give them some impressive name. Call them referees. Then you get one of these kooky articles, you will say, the referees recommend and not publish it. And Henry Oldenburg said that's a great idea. And peer review was born. And he gets credit for it. But of course, that being the 17th century, he did not give his wife credit. If indeed she made the suggestion. We can get an idea of the kinds of things that interested the men of the Royal Society by counting the papers they published. I've counted for years 1665, 1666, 1676, and 1686. And I've used modern classification. Actually, the 1665 included part of 1666. So I really maybe should have lumped those two together. But you see, we have 8 papers that I would classify in agriculture, 61 on astronomy, 62 that are biology. There are 34 book reviews. Interestingly, this was something they took very seriously immediately. 18 on geology, 17 on medicine, 46 physics, 11 on the sea and tide. Obviously, English were interested in the sea and tides because they were a maritime nation. 39 on technology. And there I put such things as improving the way to make glass, improved ways to grind telescope lenses, that sort of thing. And then there are 10 on transfusions. But you see in the 2 later years, there are 9. Because at that time, Parliament had prohibited more work with transfusions. And there were 36 that I couldn't classify. Now, who were these men who were publishing the papers? I'll give a very brief description of a few of them. This is Robert Hooke. Hooke was a natural philosopher, architect, and polymath. For 40 years, he was a curator of experiments at the Royal Society. That means that he carried out the experiments, and somebody else did it, at their weekly meetings. And one time he was curator of experiments at the Royal Society, professor of geometry at a college in London, and surveyor to the city of London, in which capacity he appears to have done about half the surveys after the Great Fire. He built the vacuum pumps that Robert Boyle used for his gas experiments. Built some of the early telescopes. Observed the rotations of Mars and Jupiter. And based on observation of fossils, was an early supporter of biological evolution. Robert Boyle, philosopher, chemist, physicist, inventor. He is largely regarded today as the father of modern chemistry. Best known for Boyle's law, which describes the inverse relationship between the absolute pressure and the volume of a gas at constant temperature. John Wallace, primarily a mathematician, he's given partial credit for the development of infinitesimal calculus. He also was involved in a method to teach deaf mutes to speak. Well, I have the wrong show. Let's close that then. I have one of Edmund Halley. Halley is an astronomer, geophysicist, mathematician, meteorologist, physicist. Best known for computing the orbit of the comet which now bears his name. He was the first to demonstrate a magnetic compass using a liquid to damp the oscillations of the needle. The Royal Society played a different and very important role in the publication of one of the most important scientific works of all time, Newton's Principia. In 1684, Hooke and Halley and Wren, all in London, were having a conversation about what kind of a force law between the sun and a planet should make the planet go in an elliptical orbit, which Kepler had demonstrated it did. Hooke claimed to have proved that it was an inverse square law, but he couldn't produce a proof. And Halley did not believe it. Well, Halley went to Cambridge and asked Newton, what is the force law that will produce an elliptical orbit? And Newton said inverse square. I proved it 2 years ago, but he couldn't find his proof. So he promised to send it to Halley. He found it, sent it to Halley. As a result, the Royal Society and Edmund Halley encouraged Newton to prepare all the work he had done for publication. And the result was the Principia, which now we get in 2 volumes, published in 1687. Undoubtedly one of the greatest scientific works of all time. And actually a remarkable production job, because in about 3 years, he got an enormous manuscript ready for publication. I want to mention one other thing. I talked about injecting blood. They inject blood usually by just cutting the vein, putting it in the tube. There was an experiment done very early, in 1665, with a hypodermic kind of syringe. And surprisingly, it was done by Christopher Wren. He used the bladder of an animal as the source, and a goose quill, like we use for pins, as a needle, and tried, not very successfully, to do injections with that. In the rules and procedures of the Royal Society of London, and somewhat later, the Academy of Sciences in Paris, we see the beginning of an organized effort to carry out experiments intended to increase our understanding of nature and to publish descriptions in enough detail that other experimenters can try to duplicate the results. I think it's fair to say that in this we see the beginning of science as an organized activity and enterprise. We're getting beyond the single investigator who does something and then maybe writes a letter somewhere. We're getting to the point where people report their work in detail, others can repeat it, they get together and talk about it, and they publish results together. In 1887, the philosophical transactions were split into two parts. One now publishes work in the physical sciences and engineering, and the other publishes work in the biological sciences. The Royal Society today has about 1,400 members, known as fellows, drawn from the UK and the Commonwealth. They include about 80 Nobel laureates. About 5% are women. Women have been included since 1945. In recent years, about 10% of the new members have been women. There's a special category for foreign scientists who are not eligible for regular membership as fellows. Anyone who is a fellow is entitled to put the letters FRS, Fellow Royal Society, after his name. Okay, are there questions?
Well, I will ask one, Beryl, and from the beginning, you could see that there are reports from things that are happening on the continent as well as, or across the Atlantic. How international was that scientific enterprise in those early days, and there was any sort of nationalistic aspect to what the Royal Society was doing?
Okay, the question is, they obviously had correspondence with people on the continent, reports from the New World. How international was the enterprise? Was there a nationalistic part to it? There was a nationalistic part. Spratt makes it very clear in his History of the Royal Society that this is English. And we'd be proud of it because it's English. But what do we expect in English? We expect them to do the best thing out. Internationally, I really can't answer that. They certainly they accepted papers from foreigners. They published papers from people in France, in Italy, and this one in Danzig. But the members, the fellows, were all English, and they still are either English or Commonwealth. An American cannot be a fellow, although there's a special category for Americans or other foreigners. So I think it certainly had some nationalistic aspects, but they did not restrict themselves at all to work that came from Britain. They could work from anywhere. But they felt that the Royal Society was special because it was English.
The Royal Society obviously was centered or focused on Europe and specifically England, but was there any kind of an equivalent collaboration or documentation of scientific events in China? Because they were doing much of this work as well.
The question is, this is focused on Europe. Was there anything equivalent in China? And the simple answer to that is I have not the slightest idea. I don't know. There are no Chinese papers published that I found in here. What the Chinese had in that respect, I don't know.
You mentioned earlier, before the 17th century, some activity in Europe and the Arab world. What was happening in the Arab world?
The question is, what was happening in the Arab world during the Middle Ages? The Arab world kept alive much of the Greek and Roman knowledge. It came back into Europe in the 12th, 13th centuries. You see the influence of the Arab world in some of the words we use. Algebra is an Arabic word. The names of a lot of the stars that we use are Arabic terms. In terms of actual physical laws discovered, I don't know of any examples. But they were doing observation and they were developing mathematics in the Arab world. Yeah.
Just to respond to your question about China, it's a great lead-in to my talk. I'm going to give it 2 weeks, because I'm going to talk about China and science and what they did or did not do. So,
Let me
stay
repeat
tuned.
that. Dr. Paulson said, with respect to the question about China, he will be talking about China in 2 weeks, and he can answer that then. I'll leave it for him.
Was there any action taken to include citizens of the Commonwealth, of perhaps the American colonies as members of the society previous to the revolution?
The question is, would they have included Americans in previous to the revolution? They were still part of Britain. It's a good question. I don't really know. I would assume they would have. From 1662 to 1776, more than a century. Now, I don't know, but I would guess that somebody like Benjamin Franklin might have been included. Because Benjamin Franklin was well known in Europe as a scientist. I really don't know specifically, but I would think it's quite possible. Was there another question over here? Okay.
You mentioned that the journal that they publish is still published today. Does it show the same distribution of topics, or has it become more specialized in what types of area of science?
The journal, the philosophical transaction, was now in 2 parts. One is physical science and engineering, the other biological. Well, the question, the philosophical transaction is still published today. Is it still the same? Is that right?
Are the topics as
Or
widespread,
the topics is what? They would have taken out medicine. I doubt very much that they would publish articles that are clearly medical, because there are many other medical journals to take those. But they publish widely, I think, on the physical sciences and on the biological sciences. What has happened with many journals is that they have split. The primary journal of the American Physical Society, which is the physics group, is the PhysRev, Physical Review. It now publishes A, B, C, D, E, 5 sections. And each one may put out something like that every 2 weeks. So you don't read the thing through. And instead of making new journals, they have section A, section B, section E. That's happened with a number of journals. As the quantity of material that we publish has increased, they've subdivided and subdivided so that people can get the part that they really want and can read. You don't have to have all this huge stack of other stuff.
Could you elaborate a little on the instrument that was invented to hold the longitude on ships?
No, I didn't catch that.
She would like you to elaborate a little bit more on the development of the clocks for the calculation of longitude, how that.
Okay, the question is, and I'd elaborate a little bit more on the development of clocks for the determination of longitude. Parliament offered this prize of 20,000 pounds at a time when a few pounds was a good annual income. For anybody who could find a way to determine the longitude for a ship at sea. A number of people tried, and the man who finally succeeded was George Harrison. Now, George Harrison built 4 chronometers. The first three were big things. They stand so tall and so big. Hardly practical carrying ship. His fourth one that won the prize is a chronometer about so big. It of course had the spring driven, and had a balance wheel, like watches had before we went on all electronic. And it was accurate enough that after a ship had been at sea for several weeks, they could still determine the longitude to within a few miles. Those chronometers that he built are on display in London, in Greenwich. And I don't know whether they're in the Greenwich Observatory or whether they're in the Maritime Museum. But they're all on display. You can find pictures of them online. And from that time on, chronometers that were similar to his were used by ships at sea. Often they carried two. I think when the Beagle sailed, the ship that Darwin was on, they carried two chronometers. Sometimes they carried three chronometers. So if they disagreed, you could take the two that were closest together and leave the best time. But it's a fascinating story of the development of technology, the development of clever ideas for how to minimize friction. Why does a watch lose time? Well, partly friction. So how do you minimize that? You have to have an escapement. So the balance field goes back and forth instead of just one way. All these things were worked out with many variations to finally get one that was satisfactory to solve the problem. And George Harrison was was John Harrison. John Harrison, not George, he saw. John Harrison did.
Later. George Harris.
Was that really the start of what we now know as Greenwich Mean Time?
Start of,
Greenwich Mean Time?
oh, was that the start of Greenwich Mean Time? No, that came much later. They were using Greenwich time, but they were, well, no, that came later. There was a dispute between the British, who wanted to use Greenwich time, and the French, who wanted to use Paris time. In fact, the French sometimes still use French time. But Greenwich time won out as the world standard. And I've forgotten when that standardization, do you know?
I'm trying to think of it. It wasn't the early 19th century, but it was at least 100 years after the period we're talking about.
Okay. At least 100 years after the period we're talking about, George.
I have a comment. There is a Nova TV show on the public TV called Lost at Sea, and it's about that search. I don't know, it was in '98 that it was put out, but anyhow, there's a website on pbs.org about this, and it's called a companion site to that show. So there's a lot of information online about the longitude, and the book's available at Amazon.
Okay. Well, the comment was, there was a Nova show on PBS in '98 about the search for longitude. And the PBS website now has information about that. And David Sovella's book is available from Amazon.
And also at the library.
And the library has a copy. You don't have to buy it, you just go to the library and have it. Okay, thank you.
Well, Beryl, we thank you for this wonderful lecture this morning. Flowers on Fourth has helped us to express our gratitude for you with this bucket of thanks.
Thank you.
And it is not only for this lecture this morning, but it is for the many lectures that you have given during the time that we've had the bucket courses. Beryl has set the bar in terms of the excellence that we expect from the lecturers that we have. And I think a lot of the lecturers have lived up to that. But you set the bar, Beryl, we thank you so very much. And we also thank Mary Lou for being his assistant in all of this. It has been wonderful having you these years, Beryl, we thank you. Well, we're going from the experienced to the brand new for next week. Cynthia Hansen, who is Associate Professor of Anthropology at the college, is going to be doing the class next week on language, the good, bad, and the ugly. And I've asked her to say a couple of words to you to give you a preview of it this morning. Cynthia?
Good morning. I am looking forward to following this lecture, which kind of gives us some of the big foundations of scientific inquiry, to talk about the field of linguistics, which most people don't know about. What is that exactly? The answer is easy. It's the scientific study of language. The hard part is defining language and what counts for this scientific study. So that's what we'll look at and talk about next week with me. I'm looking forward to it.
We will all be looking forward to it, Cynthia. Thank you. And thanks to all of you for coming this morning. Remember to turn your cell phone back on, and we'll see you next week.